Good afternoon, everyone. Welcome to BU Science Seminar Series. I'm Mike Charette, and I'm the coordinator of the MELS graduate program. I'm stepping in today for Dr. Malcolm, who can't be here. As a quick reminder, we have a seminar next week by Dr. Roberto Lingoli of the Department of Psychology at BU. Same time, same place, obviously, for that seminar presentation by the new faculty member. At this point, in terms of introduction, I'm simply going to turn it over to Dr. Oibola, who is a new faculty member in the Department of Mathematics and Computer Science at Nigerian University, who will give the introductions of today's guest speaker, since he's the host of our guest speaker.
Thank you, Dr. Mike. I think that's on. Okay. Thank you. So I want to use this medium to briefly read out the brief biography of the presenter. Is Professor Tèmitópé Gbóláhàn Jaiyéolá. He obtained a BSc degree in mathematical sciences with bias in mathematics in 2002 and his Master of Science degree in mathematics in 2005 and his PhD degree in mathematics in 2009 at the University of Agriculture, Abeokuta, Nigeria. And now Federal University of Agriculture, Abeokuta, Nigeria. His MSc and PhD thesis were based on notions of central loops and Osborn loops in the field of algebra, known as theory of quasigroups and loops. After his graduate studies at the Federal University of Agriculture, Abeokuta, he got an appointment at the Department of Mathematics, Faculty of Science, at Obafemi Awolowo University, Ile-Ife, Nigeria, in 2006. And he has since risen to the position of a full professor in 2017. He has been teaching algebra courses at undergraduate and postgraduate levels. He has supervised 9 Masters of Science in Mathematics theses, and he has supervised 7 PhD mathematics theses, of which mine was one of it. He has attended national and international conferences and schools in the past and has been involved in the organization of some others. He's a fellow of the Nigerian Young Academy, editor of Mathematical Sciences section of Annals of Science and Technology, published in Nigerian Young Academy. Also International Journal of Mathematical Sciences and Optimization, Theory and Applications, and International Ambassador of Africa Project Against Suicide. He is the head of Nigerian branch of Neutrosophic Science International Association, University of New Mexico, United States of America, and the director of Human Resources, Platinum Mines Global Company. He has published not less than 85 journal articles. He has authored a book, co-authored another book, reviewed 7 books, and contributed to 7 books. He specializes in the area of algebra called groups and their generalization and non-associative algebraic systems. His field of expertise is in the theory of groupoids, quasigroups, and loops. He also works on Neutrosophic algebraic structures and non-associative hyperalgebraic structures and soft quasigroup. He's enthusiastic to apply these areas of studies to cryptography, coding theory, sociology, sports, and biological inheritance. He's a member of professional organizations like Nigerian Mathematical Society, African Mathematical Union, and American Mathematical Society. He has served as a referee for some scholarly journals, both nationally and internationally, since 2009. He's a reviewer for the Mathematical Reviews and Central Blats. He has won some national and international awards, among which are International Mathematical Union for the International Congress of Mathematicians in 2010, and International Mathematical Union Chebyshev Grant for the International Congress of Mathematicians in 2022. As a member of the Nigerian Young Academy executive, they won a $5,000 USD towards Rosa Grant in 2016 and $25,000 IAP Courage Small Grant in 2018 and another grant in 2018 as well. And is the current occupier of Pastor Adeboye professorial chair in Nigeria at the University of Lagos. So permit me to welcome once again the presenter, Tèmitópé Gbóláhàn Jaiyéolá, for his presentation. Thank you.
All right. Thank you very much. I welcome everyone to this presentation. All protocols duly observed. I will be speaking on the quasigroups, loops, and some of their applications. Let's go. The breakdown of the outline of my talk, I will quickly take an historical background because of the nature of the audience. Bo loops, Bo Mofang type identities. Then we'll look at group-wide quasigroups and loops, some basic properties, variants of inverse properties. Then thereafter, we'll look at some concepts in group-wide quasigroups and loops. And we now finish up with the applications in physics, cryptography, and biological inheritance. The various areas in which loop theory originated during the early parts in its 90 years. So loop theory is now 90 years. We can move on, please. You can move the slide. Can be mapped in chronological order. And for instance, if you ask what is a loop, of course, to a lay person, the simplest response you can give is that it's a group that is not without associativity. Well, that is true, but it's not the whole truth, actually. And loop theory is not just a generalization of a group theory, but it has become a discipline on its own. Please move the slide. It has become a discipline of its own, and is currently moving in within 4 basic research areas: algebra, geometry, topology, and combinatorics. Let's move on. If you look at the history of loop theory, the 1920s was the first glimmering non-associativity. As we all know, the oldest non-associative operation you can talk about is subtraction of natural numbers. And thereafter, after 1930s was the defining period. And the 1940s to 60s was the period in which the basic algebraic frame were used. At this point, the United States became the center of research of the subject, and that was actually where the name was inherited. Let's go on. And that was where the name loop arose from the Chicago loop. The 1950s to 60s saw the return of loops to Western Europe, and the combinatorial aspect started developing, Steno triple systems and the likes. And in 1950s to 60s was the ascendance of loop in the Soviet Union. The book of Belozov, which is a very, very precious to those in that region, written in 1967, can be compared to the book of Brock. Let's go on. Now we saw the birth of loop theory in Africa, and this is courtesy of, especially in Nigeria in particular, this is courtesy of B.L. Sharma, an Indian, and A.R.T. Sholarin. They worked extensively on the study and construction of finite Bo loops of various orders. And this took place in the same institution I am currently located, that is Obafemi Awolowo University. Later, Oji Adeniro joined the research team of Professor Sholani and Shama. And after Professor Shama left Nigeria, the duo of Sholani and Adeniro moved from OAU to the University of Agriculture, Abeokuta, UNAB, now FUNAB, where the study of loop theory continued. And this was where myself, Jaiyéolá, Oyebo, Ishere, and few other Nigerians encountered quasigroups and loop theory. I met Oyemi at Oyemi met me at OAU. So, and in fact, we are having a valedictory conference we'll be organizing in month of April in honor of Professor Sholani, who will be 70 years this year. Prof is is online with us. He's glad to have him listening to this talk. Now, between 1920 and early 60s, two particular classes, let's move please. Two particular classes of loops were the most popular, Mofang loops and Bo loops. And Phoenix in the 1968 and 69 did a classification of what he called loops of Bomofang type. That is, those loops that are described by identities that look like the identity of Bo and the identity of Mofang. That is, those identities that involve the three distinct variables on both sides, containing variables in the same order on both sides. Exactly one of the variables appears twice on both sides. He discovered that 30 of them are actually equivalent to associativity, and the other 30 describe varieties of loops of Bomofang type. So among these are your left and the right Boole identity, Mofang identities, central identities, extra identity. In 2005, Phillips and Fojoski took a general look at the work of Phoenix, and they completed it by actually finding examples. And initially, Phoenix came with just 3 identities, equivalent identities that describe the left and right central loops. But the duo of Phillips and Fojoski came up with a 4th one for each. And there are 4 equivalent identities that define Mofang loop, 3 that define extra loop, they are equivalent, 4 that define, and you have the left or the right Boole loop, and the central loop stuff. In 2022, myself and George reported that what we call second Bomofang type identities in loops. In this case, these are identities of length 5, and 4 of them were found to be new loop identities, which individually characterize Mofang loop. Thus, we now have 8 loop identities that characterize Mofang loop. So the list of identities that you can see above are loops of Bomofang type, and they are named accordingly. Let's go on. As you can see, there are 4 of them that describe left central, 4 right central, 4 of them, 5 of them, 4 of them Mofang. And please, let's move the slide. If you take a look at that ACE diagram, over the years, people have done research on these various classes of loops and the relationship among them. Interestingly, a group implies all of them. A group is an extra loop, is a Mofang loop, is a central loop. So that is why we call them generalization of group. But they are not necessarily a group. But under some conditions, they will become a group. When you look at this picture, philosophically, it paints a picture of the goal pole, and why the group stands in a position of the penalty spot, so to say. So which means for any result you get in loop theory, especially loops of Bomofang type, a group will satisfy all of such. An extra loop is a Mofang loop. It's also a C loop. In fact, a loop is a Mofang loop if and only if it is both a Boole loop, a right Boole loop, and a left Boole loop. A loop is a central loop if and only if it is both a right central loop and a left central loop. And there are some other conditions you can have to move-on that will make it extra. A loop is an extra loop only if it is both a move-on group and is conjugacy closed loop. And a loop is also an extra loop only if it is both a central loop, that is C loop, and CC loop. So these are very interesting relationships. Above is the list of notable books in Quasigroups and Loops. There's of recent, Sholani and Sholani, Adeniro, myself, Oyebo, and Isheri published a book chapter, in a book published by Springer of recent. And now let's see what is a quasigroup, what is a loop. Given a non-empty set, if you put a binary operation on it and it is closed, then you call that pair a groupoid. And if you have a groupoid and those two particular equations that you can see in a second definition have unique solutions for x and y respectively, then you have what we call a quasigroup. And if you have a quasigroup and there is a unique element, which we often denote by E, such that x dot E equals to E dot x equals to x, for any element x you pick from the non-empty set L, then you have what we call a loop. And just to give an example of finite loops, finite groupoid, quasigroup, and loop, if you look at that first multiplication table, please, let's move the slide. A, the multiplication table A shows a groupoid. It's a groupoid because based on the multiplication, you can see 1.1 is 1, 1.2 is 2, and so on. All cells are, no cell is empty. All cells are filled up. So which means there is closure property and the entries in the cells belong to the set 1 to 5. And so that's a groupoid. But it is not a quasigroup, because if you discover that those two equations are not necessarily satisfied, and you get to know that because you can find repetition in at least a row or a column. For instance, if you look at that table very well, you will see that 3.1 is 3 and 3.4 is 3. So in that case, now you have a violation. So, but if you look at the second one, B, is a groupoid, is a quasigroup, because those two equations are satisfied. For a finite system, finite groupoid, you can easily know whether it forms a quasigroup or not if there are no repetition in any row or column. If you look at all the rows of and columns in that particular multiplication table, there are no repetitions. You call such kind of table a Latin square when you unborder it. The second one, but unfortunately, the B, that multiplication table, which represents the quasigroup, is not a loop, because there's no element that satisfies, there's no element that plays the role of E. That is an element that obeys x dot E equals to x equals to E dot x for all x. No element. But when you look at the third multiplication table, you will see that 1 plays the role of the identity element, because when you use 1 to multiply all other elements, you get them back accordingly. And when you use all other elements to multiply 1, you get them back accordingly. You can easily see that when you look at under the row and column in which 1 is, you will see that all other entries appear accordingly. So for finite algebraic structures of the type binary system, this is how you can quickly check whether a groupoid is a quasigroup or a loop. And it must be noted that all Latin squares of orders from 1 to 4, they are all associative. You begin to have non-associative loops from order 5. Let's move on. There are some tools we use in the study of quasigroups and loops, and some of them are your left and right translation. So, but because of time, I won't be able to talk too much about this. This is just a seminar, and because of the nature of the audience. And we also talk about, just like you talk about the inverse of an element in a group. We all know that for any element in a group, there exists an element x raised to power minus 1, which we call the inverse. Next slide, please. Such that x dot x inverse will give you x inverse dot x will give you e. But when it comes to loops, you may have a left inverse and a right inverse as defined. We represent our left inverse by x lambda raised to power lambda and the x row as x as the right inverse of x. So you need not, x lambda and x row need not be equal in a loop. But for a group, they are always equal. And you can also talk about, in a quasigroup, you can talk about x lambda and x row when you have what we call a right identity, left identity, or even for groupoid, when you have what we call local identity, sort of. We won't be able to talk too much about this also because of the nature of this presentation. But these gaps, the gaps between quasigroups and loops, groupoid and quasigroup, the gaps among them can actually lead to some other kind of algebraic structures. We call them Neutrosophic algebraic structures. But we won't be talking about that here. Let's go on. Move on, please. Move on. There are some subsets of a loop. For a non-empty, a loop that is non-empty, we talk about the centron, the set of those elements that commute with others. And there is also what we call the nucleus of a loop. Sorry, I didn't put the definition here. In fact, interestingly, since a loop is not necessarily associative, we talk about the left nucleus, the right nucleus, and the middle nucleus of a loop. That is, the set of elements that associate with others from the left, the set of elements that associate with other elements on the right, and the set of elements that associate with all other elements from the middle, sort of. So the intersection of the left, the right, and the middle nuclei will give you what you call the nucleus. And the intersection of the nucleus and the centrum of a loop will give you what you call the center, Z, of a dot. It must be noted that in the case of a group, the nucleus of a group is just a group. So the nucleus is not interesting to us in a group. But for loops, is of interest to us. At times we look at the structure, will it be normal or some other things? And you have what we call the symmetric group of a loop. Okay, let's go on. Now here are some basic loop properties. Next slide. Most of these properties are trivial in a group, but in what we are studying here, they are not necessarily trivial. Take a look at you have what we call the left alternative property, right alternative property. Okay, you can see that these are all two variable laws. Next slide. You also have what we call the left inverse property. Okay. Next slide. Left and right inverse property. Okay. Of course, if there is associativity, all these are trivial. But because of non-associativity, they are not necessarily trivial. And you also have, relative to the inverse property, you have what we call the weak inverse properties. They are variants of inverse property. One of them is the weak inverse property, WIP, and another one is the cross inverse property. Okay, we'll be talking about the cross inverse property because we will find it applicable to cryptography as we go on. There are some other ones: automorphic inverse property, anti-automorphic inverse property. We also have semi-automorphic inverse property. Let's go on. Can you please move the slide? Okay. Let me quickly just talk about some concepts in loop theory. Given a loop, in fact, G dot, if it's a groupoid, if you have a triple, UVW, triple of bijections, and if they satisfy that particular condition, as you can see, please move the slide to orthotopism. Next slide. Next one. Okay, so you call such triple an orthotopism, and if you are in a group, of course, you know we don't talk about orthotopism in groups. In the case of a group, you have what we call an automorphism if those three triples are equal, and you also have some other ones. If the three of them are equal, move the slide, please. If the three triples are equal, you have an automorphism, and you also have what we call isotopism. given two loops or even two quasigroups or two groupoids, if you have a triple, please move the slide. Triple of bijections from L to G, mapping L to G, okay, satisfying that condition, you call it an isotopism, and you say those two loops are isotopic. And if the three of them are equal, you have what we call an isomorphism. And we have particular special kind of isotopes, which you call principal isotopes under principal isotopism. So, and we also have what we call an holomorph of a loop. Let's go on. Please move the slide. So I go to application now because of my time. Please, I have how many minutes more in order to guide myself? The first application I'll be talking about, please move the slide. The first application I'll be talking about is in physics, Hastings relativistic admissible velocity vectors. Among mathematicians and physicists, symmetry is thought as being virtually synonymous with theory of groups and its action, but unlike the velocity addition in non-relativistic setting, the Hastings velocity vector is not a group operation because it is non-associative. So this is very interesting to us. And however, owing to the presence of the Thomas precision, there's no loss of mathematical regularity. Now, if you, next slide, please. If you consider the sets of relativistically admissible velocities, which are elements of the open ball house C cube, and you put a binary operation, O plus E, which is called the Hastings velocity addition. If you put it on it and define it accordingly, you are going to have a non-associative structure. Go on, please. Move the slide. And this has been of interest to us in loop theory. And this led to what you call a gyro group. Please move the slide. A gyro group. A groupoid. A groupoid is called a gyro group if it obeys the following axioms. Left identity. Can you please move the slide? Left identity, left inverse, then the left gyro associative. When you look at the left gyro associative axiom, you see that when the gyration of x and y is I, that is the identity map, you are going to have associativity. Okay. So which means you can measure non-associativity in a gyro group via the gyration. And here's an example as given. Next slide, please. Please move the slide. A. Younger did a lot of work. He has some books on this. And he has some results, existing results on gyro group. They write gyro associative law. They write loop property. And in particular, you will see that some of the axioms of quasigroup are obeyed. For instance, look at that existing result on gyro groups 2. You see that the cancellation law holds both the left and the right cancellation law, and the left inverse property is obeyed. So, in fact, your gyro group is actually a special kind of a left bow loop. And gyro groups are a type of left bow loop. Okay. And they have been found to be related to some other kind of loops, such like K loop, Brock loop. Can you please move the slide? And we took interest in the gyration of gyro group at some point. Please move the slide. And we were able to characterize some of the basic loop properties in the gyro group. That is, we wanted to know, when will a gyro group have weak inverse property, flexibility, wrap, and we discovered that it is when the gyration, okay, of xy acts on x, that is fixes x. Okay, and we also investigated some other properties as well. That was in 2014. So that is that application to physics. Now I go to cryptography. I mentioned earlier on, please move the slide. I mentioned earlier on that one of the type of quasigroup or loop that was introduced then, called cross-inverse property quasigroup, will be of importance. Please go slide before. Just go backwards a bit. Now there is what we call what I call the Kidwell cross-inverse property quasigroup. Kidwell in 1999 was able to develop a method of constructing cross-inverse property quasigroup using an abelian group. So giving an abelian group of order n, such that n plus 1 is composite. If you define a binary operation on G by that given relation, okay, where your RS is equal to n plus 1, then G sec is a cross-inverse property quasigroup. And the right cross-inverse of the element is given by that. Now, what make cross-inverse property loops and quasigroups to be appropriate for cryptography is that they have what we call long inverse cycle. Next slide. They have long inverse cycle. That is, we all know that for your inverse property, even in a right or left inverse property loop, the inverse, when you find the inverse of an element, you get that element back. But in the case of cross inverse property, the inverse of an element is not necessarily that element. For you to achieve, when you find the inverse of an element, okay, repeatedly, you discover that it could be after a long cycle, and that is what you see there. So that is what makes cross-inverse property good for cryptography. So they have what we call the cycle theorem for them. Now we came up with, using Kidwell cross-inverse property, he had described a method of applying cross-inverse property loops to cryptography. But in order to strengthen his method, we decided to come up with isotopy. We introduced isotopism. That is, we consider two quasigroups. Okay? And we consider their holomorph. And we discovered that their holomorphs are isomorphic if and only, please move to the next slide. Their holomorphs, that is H of U, H of V, are isomorphic if and only if they are isotopic. And using that particular theorem, next slide, in 2012, we were able to show that an automorphic inverse property quasigroup or cross-inverse property quasigroup or loop, okay, will be invariant. The property of AIP or CIP will be invariant for quasigroups or loops with this particular property. So, and we're able to adopt that to do what we call, next slide, a double cryptography using the Kidwell cross-inverse quasigroup. Please let me know the number, how many minutes I have more. Okay, and in applying it, you have to get an appropriate cross-inverse property. Some of the ones constructed by Kidwell were found appropriate for this. So after getting an appropriate one, the next thing you do now is you take, based on our theorem 3.7, by the choice of the map, please move on, alpha and beta from the automorphism on U, next slide, and gamma, psi from the symmetric group of L. So the secret key for the system will be that triple, okay, related to delta gamma, the triple of alpha, beta, psi related to delta gamma, to that pair. And Thus, whenever a set of information or message is to be transmitted, the sender will encrypt in the Kidwell cross-inverse operator quasigroup and then encrypt again using those mappings to get a cross-inverse operator quasigroup V. Okay? And at the receiving end, the other person will decrypt using the inverse of the process as described to get the message. Okay, so that is that on application of quasigroup and loop to cryptography. The next application I will be talking about is in biological inheritance. But in this case, I'll be talking about this in respect to hyperalgebraic structures. Algebraic structures are suitable generalization of classical algebraic structures. As you all know, in your classical algebraic structure, the composition of two elements is just a single element. But in the case of algebraic hyperstructure, the composition of two elements is actually a set. We are much more interested in when it's a non-empty set. So now, genetic algebra, as at 1939, there was a presentation on genetic algebra, non-associative algebra, and symbolism of genetics. In 1941, Shabbat published the structure of genetic algebra in 1949, and we have been able to show that non-associativity of hyperstructures are associated with inheritance. Some authors have explored, let's move on, please. Some authors have explored the algebraic hyperstructure that naturally occur as genetic information gets passed down through generations. They are generally commutative, but not associative. And we have the works of Davas et al. And Tahan on hyperalgebraic structure and the application to biological inheritance. So our own interest here is actually to track down. Yes, they were able to show that you can represent the outcomes, the genes, the interaction among the genes. You can represent them in form of hyperalgebraic structure. But we are more interested in, yes, they are hyperalgebraic structure, non-associative, but are there particular properties, weak associative properties that are satisfied. For instance, take a look at the blood group inheritance with MN antibodies in human. MN blood is unique from the long familiar blood groups. Okay, now take a look at that table. That's an hyperalgebraic structure. And if you begin to, please move on, if you begin to investigate this particular structure, you will see that if you check associativity, it is non-associative. You find a triple that is non-associative. Okay, and if you check some of our weak associative laws, in particular the first extra identity, you will discover that for that particular triple it is satisfied. Okay, if you go on, please move on. If you go on and check it for the second extra identity, you will discover that it's not satisfied for a particular triple. And for a third one, it's also not satisfied. So the moment associativity breaks down, we are usually interested in weak associativity. Okay, variables of three, identities of three variables or two variables which do not necessarily imply associativity. So we are still working in this direction in order to get a precise measurements, okay, of weak associativity in a biological system, and by extension to chemical system. We have work also going on some chemical systems, okay, that can be represented by hyperalgebraic structures, and we are also investigating. Work is still going on those ones as well. Thank you so much for listening. These are my references. Thank you.
Okay, thank you, Professor Jaiyéolá, for that presentation. Does anyone have questions based on the study so far, the presentation? Any question? Okay. Okay.
Well, mine will actually be a kind of recommendation. Prof. Tèmitópé, I think, if I'm certain, it was one of the guest speakers in one of the seminars I attended, the MAN seminar in Lagos, MAN Mathematics Lagos chapter. Yeah, so he was actually a resource person. So, Prof, please, what are some of the real-world application or example where quasigroups or loops are used to model or solve problems?
Yes, I just discussed 3 of them. Well, I discussed application in physics, in cryptography. Okay. Though unfortunately, because of time, I can't. There are so many works have been done related to cryptography. So many works have been done. So not only cross-inverse property, you can also use Osborn loop. We have been able to come up with what we call cryptographic identities. Okay.
Yeah.
All right. So those are some of the real life examples. Then in biological inheritance.
Yeah, just as you point out, will not be actually enough to exhaust that, because I have some issues in even in that application in physics, for example, in electricity and in some quantum physics, how to basically use the quasigroup to solve a real world problem. But I think you have been able to demystify some of these, and it's quite interesting. Thank you.
Okay, well, how do you get to know whether you can apply quasigroup to a problem? The question is does the system portray non-associativity? That is a very important question you need to, first of all, ask yourself. Because the moment the system is associative, then you may not be able to apply quasigroups and loops. But if you can show that the system, if you observe non-associativity in the system, then quasigroups and loops can possibly come in.
And can there be a kind of commutative?
Yes, there could be commutativity.
Okay.
Yes. A quasigroup can be commutative and not necessarily associative.
Okay, yeah.
Okay. Yes.
Thank you.
And just to add to what Prof rightly said, he has also been able to also apply the concept of Neutrosophic to sports. So, and he has a publication on that as well. And for the biological inheritance, it's one of the things we have been able to do together. Even my PhD thesis was centered on the applications of that concept to biological inheritance. Good.
Do you mind elaborating on this application to sport? I'm
Okay.
Curious.
So,
or
Prof,
the professor as well.
over to you. You have some minutes to do that. Some of the work that
Okay, all right. To sports, you can consider the set of players in a team, okay, as the element of, let's say, a quasigroup or a loop. Now, we all know what associativity means in real life. You need 3 variables. When you look at the law of associativity, 3 variables are arranged on both sides accordingly, but paired, okay? And that simply means that depicts understanding. X, Y, X multiplying Y, then multiplying Z, equal to Y multiplying Z, then X now multiplying YZ. At least if we have 3 players, whereby the binary operation depicts passing of the ball accurately, the 3 of them, whether player X, first of all, passes the ball to Y, player X passes the ball to Y, by the time the ball is passed to Z, Can you compare that? Their understanding. Okay? Can you compare that with when the ball is first of all passed from Y to Z and then between X and that? You can look at it from that particular angle. Okay? A breakdown of associativity, okay, is like a breakdown of association, means understanding, sort of. So we've seen in the game of soccer of teams in which you have two particular players or three particular players that form the core of a team, whereby they are actually the engine room of that particular team. So you can use that to understand, to come to unveil the understanding. If you are probably the coach, the manager of the opposing team, and you really want to break the communication among two or three players, you can use the understanding of weak associative laws in order to unravel how to use your defenders to break the communication among three particular players at a point in time. Something of that nature, but it's something you need to go very deep into in order to comprehend very well.
So I just put that on the board. Thank you, Prof.
All right, thank you.
Okay, there's a question online. I'm not sure if you can see it in the chat.
Okay, I can see. I'm looking at my chat now.
So I'll maybe just read it out so the folks in the room can see it as well. Wonderful presentation, Professor. I've been considering relationships of some of these concepts to the game of chess. Can you help unveil this? Do you mind speaking to that?
Yes, there's nothing that is impossible. All you need to do is, okay, like chess, though I'm not too much familiar with the game of chess. All you need to do, the players, what you use in chess, the elements of the set now becomes what you use for the game of chess. Then the rules, you have to look at the rules guiding as well. From the rule, now try to look for appropriate quasigroup, because, for instance, you have so many identities that describe, you have varieties, so many varieties and classes of quasigroups and loops. So you now try to look for which class or variety of quasigroup of loop have properties or have identities that sort of describe, that sort of fitting into the rules. Because one thing I know is that in the game of chess, what you play with have how they can move, what you can use them to, okay, there are limits set on their movement. So that is what we need to do. We need to marry the two together and see and look for the appropriate one. Yes, someone just said, basically from the multiplication table you displayed. Yes. Now, a good question to ask is, from a multiplication table given, can I know the algebraic property satisfied? Can I even know what type of quasigroup is this? Or what type of loop is this? Actually, literally speaking, you cannot know, except you take it through, you check the property or the axiom, the law, and you can do that using writing some quotes in some special packages like GAP to check it. You can do that. But this is another area when you now go into combinatories, that launches, because combinatories has a lot of interest in the study of Latin square. So when you say, if your interest is in the multiplication table based on the arrangement of the elements, then that falls under combinatories. So you now begin to look at, is there a way you can marry how entries are arranged in a multiplication table? Is there a way you can formulate the behavior of it? Something of that nature. So it's possible, not it's impossible, but you still have to do a lot of study in that respect. Thank you.
Any other questions? Number of thanks online. Any questions in the room? Okay, I think we will. I'd just like to extend a huge thank you for joining us and yeah, sharing a really interesting talk with us. Much appreciate. I'll let you have the last word. You can go ahead.
Thank you very much. So I want to use this medium to appreciate you, Professor Tèmitópé Jaiyéolá, for finding this time out of your busy schedule to be part of us this afternoon here. I know it's very late in Nigeria now, so it's about 10:30 in Nigeria, 10:30 p.m. So I want to also use this medium to appreciate everyone online for being part of this, and everyone in the room as well. So thank you so much, and do enjoy the rest of the
I want to appreciate Professor Shulani and my professors, Shulani and Professor Adinino. They're online.
Yes, and that's Professor Adewale Shulani happened to be my academic great-great-grandfather. So Professor Olushola John Adeniro is my grandfather academically, and that is Professor Adewale Shulani. Prof, you are welcome, sir.
Good evening, everybody. It's my pleasure.
Thank you so much. Prof will be having his retirement come April, so we hope to have a nice celebration for him. Long may you live, Prof.
Amen. Thank you.
Thank you so much.